Well, hello. This will be our fourth video on static and dynamic light scattering, but finally we're going to focus a little bit on the dynamic light scattering. And in order to do that, I should tell you about why it is so important. You know, static light scattering that we've been discussing works for almost any molecular weight you can think of, all the way from sugar molecules, which are pretty small. If you get them up to high enough concentration, you could get their molecular weight from static light scattering, all the way to virus particles, which you can see here are 41 million grams per mole. Pretty heavy stuff. And if it was just a matter of getting the mass, static light scattering would have everything covered. But when it comes to getting size, we're limited because of the long wavelength of the light compared to the object we're trying to see. So everything has been about phase shifts, and it all sort of depends on the size of the object we're trying to study compared to Q, that scattering vector magnitude. And so one way to get around this is to go and do small angle X-ray scattering or small angle neutron scattering. You could just shorten the wavelength. Both X-rays and neutrons that we have available to us have very short wavelengths. In fact, they're so short that now you have to go to very low angles, or the phase shifts will be incomprehensibly large and you won't be able to straighten it all out. Unfortunately, these instruments are sort of expensive and fussy, and they don't sit on a bench top. Hardly. A neutron scattering facility might sit on a football field or something, you know, comparably sized to that. And the really powerful X-ray machines are that way too, but there are lab-based X-ray machines that you could use, but they're a little bit difficult to access, and there are some other problems with dealing with solutions of polymers in those systems. So if you just need a size, okay, if all you really need is a size and your material is too small, let's say lambda over 50 or 10 nanometers. If it's 10 nanometers, even 15 or below, it's probably time to really think about one of these other methods. And dynamic light scattering is just one of them. There is fluorescence photobleaching recovery, fluorescence correlation spectroscopy, particle tracking may sometimes work, analytical ultracentrifugation, okay, or what's called DOSY NMR. This is a form of NMR. Of course, there's good old viscosity, which works pretty well for very small objects as well. So you have a lot of options, but sort of the one that catches everybody's attention because it's so quick and fairly powerful and relatively easy to do is dynamic light scattering. And the premise of this method is basically that if it moves, we can tell how fast, and then we convert the speed of the object into a size. We're using a pretty reliable relationship, a very reliable relationship, in fact. So we're going to look mostly at dynamic light scattering. And what I would encourage you to do is to go back or think back to when we were talking about phase shifts. So this figure here, we've already seen this figure on the left. And we have, you know, some scattering blob. It's some sort of giant protein or aggregate, or maybe it's just some sort of, you know, weird shaped polymer at one instant in time. And it has a subvolume A and a subvolume B, and the scattering through A and the scattering through B could be out of phase and destructively interfere, you know, whether fully or only partially, doesn't really matter. So we're used to the idea that, you know, things that are in different locations lead to a phase shift, and this in static light scattering, you follow that phase shift as a function of angle, and you back out something like the radius of gyration. In dynamic light scattering, I want you to think that we have the same particle, A, at time t prime, and a at some time t prime plus some later time t. And this little t here is called the lag time, the lag between t prime and t prime plus t prime, t prime plus t. So this is the lag time, and during that lag time, the same molecule is moving around. So in dynamic light scattering, we're looking at these phase shifts off of one scattering element and another at different times. And in fact, you see that I've erased the red thing here. So these could be very small particles, not on the same scattering object at all. Over here on the left, we're imagining that, you know, A and B are part of the same scattering entity, only in different locations. Here they could be totally different, distinct particles. And they can be small because we're really looking at giving them, the distance really comes from the time, you know, that they're diffusing around. They change their distance, so we get the distance we need to see a phase shift is provided by waiting. And I mean W-A-I-T-I-N-G, okay, a delay. Okay, so what we'll do now is we'll sort of look at this dynamic light scattering problem from the standpoint of a particle scattering development. So what you see here are 1, 2, 3, 4 particles, and they don't normally stand still like that. They normally diffuse. We'll put them in motion in a minute. Over here, off to the left, is a laser beam, and it sends light and hits those particles, and then the incident beam is, you know, goes in that direction. And over here, at some angle theta, we'll place a detector. Now, when the particles go into motion, they move, and you can see in little areas where they cross that their fringes represent their scattering. You can see that they make kind of a moire pattern, M-O-I-R-E, moire pattern. But the overall light scattered towards the detector is constant. Okay, it's only in little regions where we see that sort of interference between the scattered rays emanating from each of the 4 particles. So since we, you know, look at everything, we look at too much here, we look at a large volume, a large area here, the intensity is constant. Okay, the intensity is just constant. So if we want to see the fluctuations, we have to look at a smaller area. So let's put in a pinhole. Let's just look at one little area. This should do it here. Here it comes. There's a pinhole. And you can see behind, now and again, you'll see a particle go looping. There it goes. Okay, so they're still diffusing back there, but we're only looking at the light through this little hole now. Okay, and what it does in that little hole is fluctuate, and the rate at which it fluctuates is inversely proportional to the size. Very large particles that diffuse slowly fluctuate slowly, and very small particles that diffuse quickly fluctuate rapidly. So it looks like a random signal, but in fact nothing is completely random. Nothing in the whole wide world is completely random. I could just as well have made this plot be you know, the value of my stock portfolio. It goes up and down too, but if it's really, really high, you know, at 12:01 p.m. today, my stock portfolio is really, really high. Then a short time later, let's say 12:01 and 1 second, it probably hasn't nosedived completely. So nothing is completely random. So a completely random variable would go from, you know, plus 10,000 to minus 10,000, you know, in femtoseconds. So it doesn't do that. It stays correlated with itself for a while. And one way to follow this correlation is with the thing that's called a correlation function. Now this is an autocorrelation function. It is a correlation of the intensity with the intensity at a later time. And so that's what I was saying a little bit earlier. We're going to be looking at phase shifts at one time compared to phase shifts at a later time, and the manifestation of those phase shifts is these intensity fluctuations. Okay, so the intensity just fluctuates with time. Now, there are a lot of t's in this equation. So let's talk about the t's. T prime, okay, is actual time. It's the actual time at, it's like 12:03 p.m. plus 5 milliseconds or something like that, It's an actual time of the day, or the actual time. And little t with no prime, that's what's called the lag time. It's the difference between the times when you sample the intensity. We're going to get the intensity at time t prime, and then we're going to get the intensity at time t prime plus a little bit later. And the integral says do this from, a long time ago to a long time into the future, because we're going to take this big T, like the acquisition time of the experiment, we're going to get it to be infinity, or as long as we can bear, as long as we can tolerate. So in a typical dynamic light scattering experiment, this big T that's supposed to go off to infinity is more like 60 seconds, maybe 5 minutes, 300 seconds, maybe more, depending on how fast the system is evolving. Okay, so the actual thing that sets the experimental times that we choose for big T here is how quickly the system is evolving itself. We have got to let the system do many fluctuations in order to assess how long it stays in one state, more or less. So again, the idea of the correlation function is to look at a signal that's fluctuating, not randomly, because nothing is random, and see how long it stays correlated. Okay, if it's down, how long until it's up again? How long does it stay down? Okay, if it's up, how long does it stay up? Okay, so that's the idea of the correlation functions, and these signals have a characteristic time. And we can use that time to assess how fast the phases are shifting, and that is happening because the molecules are diffusing. So what's going to come out of this is a diffusion coefficient. Okay, so this signal, it turns out, is an exponential decay. It sits up there on a baseline of 1, and then it has, a parameter f times an exponential, and it has a decay rate gamma, actually 2 gamma is the decay rate, and this gamma is q squared, that's the same q that we've been talking about, times the translational diffusion coefficient. And so what this technique really measures is the translational diffusion coefficient. And it turns out that that's inversely related to the size of the particle by a very reliable function. So now, I stressed previously that if there's a particle view, there's also a wave view. And so here again are some waves taken from the bow of a ship that I was on at the time. And it's too bad it was a cloudy day, but you'll have to take my word for it. The sun, such as it was coming in the direction shown. And it gets reflected off of these waves. And the waves move, okay? And so the light fluctuates. And you'll notice that there are little tinier waves over here that are oriented a little differently, and not as much sunlight is getting reflected off of those. But if it were being reflected off of those, we would expect those to be rather rapid fluctuations because we are at shorter distance scales. These little ripples change more quickly than a big swell like that. These are actually the wake of the ship you know, the ship is actually going out to sea in this case. It's going that way. And you can see it's sending off bow waves that are going to go here. And actually those travel a long way over to the shore. That's, if you ever sat on the shore when a ship went by, you notice that the waves do propagate a long way. But anyway, a light that was reflected off of those waves would fluctuate sort of at a different speed than it does at high Q. Believe it or not, that's kind of related to Fick's law of diffusion. Okay, so here it is, the same situation again. I think this time I'm going to try to ship into a pointer, laser pointer, and then I should be able to actually see these waves. And maybe you can even hear the video. It's a windy day. Okay. And the total amount of light reaching my eyes when I was standing on this ship was constant. Okay. But what I can do is I can put in a little mask here and just look at the light in that one little region, and you'll have to take my word for it, it fluctuates. You might not be able to see this very clearly, but I can see that there are little tiny fluctuations in that region. Okay? So a dynamic light scattering machine is required to make it possible to limit the acceptance of light down to where I can see those little fluctuations. And this is a classic design. This is a classic design built by a guy designed originally by a guy named Ken Langley, and he was a genius when it came to doing these kinds of things. And we built one of his systems, and still in effect, still works great. I think nobody ever did a better system. So it starts with a laser. NDF here is neutral density filters, because maybe the laser is too bright for your sample. You might have too much light, and then the light is focused. Sometimes there's a polarizing element here, and it's usually matched by an analyzer over here. There's sometimes a diaphragm there. The sample is here in this little center. And this thing that surrounds the center, is filled with toluene usually, or some other liquid that matches the index of refraction of the cell. In all kinds of light scattering, it's very important to exclude stray light. And so scattered light is much weaker than stray light or reflected light. If there's any scratches or just simple reflections, you want to try to minimize those reflections. And so the sample here is in a glass cell. So we put it, the glass cell containing the sample, we put that inside of a vat, and then the refractive index of the glass of the sample cell is matched by the refractive index of this liquid very closely, and so we cut down on one possible source of reflection off of that. And also we can use slightly scratched cells if this is the case, but it's usually best not to have scratches on your cells. Over here the light gets scattered, and these things here, AP, that's like a pinhole, or it's like, it's a hole. It's a little bit bigger, so we call it an aperture. And then this one back here is the pinhole. And those two things set up how much we actually see in the sample. Okay, so whether we see the whole scattered light of all the particles looking over everything, oh my God, with no what's called spatial coherence, and we just get a nice steady signal, or if we put those a little bit smaller, then we'll start to see the fluctuations, and we need those fluctuations to get the size. Okay, we get the diffusion coefficient, which then gives us the size. After all that, it goes off to either a photomultiplier tube or an avalanche photodiode detector. Actually, it turns out that the tubes are still higher performing than the avalanche photodiode detectors, despite all the progress in solid-state electronics. There's a preamp discriminator, there's a photometer over here, a correlator, and of course it's tied together with a personal computer. So that's what the system is, and we can see one if you want. Again, here's our equation, and let's look at it again. And actually, I would strongly encourage you to, if you're just watching this as a video, write it down. I really hated to give this lecture kind of only in PowerPoint mode. Normally, I kind of wing this lecture. Maybe it's better that way. I don't really know. But it is really good to write these equations down. It builds sort of that muscle memory, you know, the way you can remember an equation like this is writing it a bunch of times. But it's really a recipe, you know, any equation is kind of a recipe. This one says, take an intensity at some time t, multiply it by an intensity at some later time t, plus t prime. Okay, I think I said it wrong. Make an intensity at time reading at time t prime, make another one at time t prime plus t, and compare them. And comparing, in this case, comparing means take the product of. So this thing is actually understood easily in two limits. Let's see if I can get a... We will try to draw something. Okay, we will try to draw something and see if it works. Let's take two limits. What would happen if we let little t, the lag time, so we say if t is equal to 0, this g2 of 0, this thing is going to be really the intensity of t prime at t prime times the intensity at t prime. If t is 0. It's really kind of some kind of average, isn't it? I mean, it's going to take these two intensities over all possible times, divide by the total time of the experiment, voila. This must be something like I squared. Okay? And if t is infinite, okay, I should put an equal sign there. I should put one here now. This turns out to be I average squared, okay? Because if the lag time is infinite, then there's really no relationship between the intensity at some previous time. Okay? So what you get is sort of the average squared. And what you get when t is equal to 0 is the average of the squares. So which do you think is bigger? Well, just think of any numbers that you want. It's always going to work out that the average of the square is bigger than the square of the average. I can make a little argument for you along that line. Suppose instead of I being the intensity, suppose it was the current through an AC line. Okay, so here's current. And the current through an AC line, you know, alternating current line, just a wall outlet, any old wall outlet you want. That current, you know, does that. The average current, you know, the current through an AC line, it goes left and it goes right and it goes left and it goes right. And it does this at 60 cycles per second here in the United States, 50 cycles per second in many other countries. But I think you can see that the average here is 0. And the average of I squared, well, that's this. Right? So I squared is always positive. So clearly in the case of this kind of signal, it's clearly true that I squared is bigger than I average squared. Okay? And if I were to lift this and put on some sort of DC bias here. So here's 0, and I do my current here, and I do this. So now I have some sort of situation where the average current is not 0. It's still true. It's still true. Okay, it's still true that I squared, average of I squared is bigger than the average of I quantity squared. It's still true. So this correlation function, evidently as we go from lag time 0 to lag time infinity, undergoes some kind of decay, and it works out, and we're not going to prove this. That would be the function of 6751 polymer physical chemistry of solutions to do that. To prove that that is an exponential decay, but it is. Okay. So what we're going to expect is a signal that decays over time, lag time t, and it's going to start at 1 in this notation, and it's going to start out here and just decay exponentially. And the value of this intercept here is going to be 1 plus FCOH. This FCOH parameter here, this is actually called the coherence parameter. And it's mostly a measure of how well your optics got you looking at just a few of the fluctuations, how well you could observe the fluctuations. There can be some other electronic things that go on and affect that parameter here, but it's called the coherence parameter for a reason. It's measurement of how coherent you've made your optical field, because that's what it really takes to see those fluctuations. Okay, so the fluctuations they actually look like speckles. And we can go down to the lab and you can see them yourself live. But we took the effort a summer or two ago, we made the effort to record these for you. And so if all goes smoothly here, we should be able to watch some recordings. And I would encourage you to do it, but we'll just watch it a little bit. Let's see what happens. Okay. Oops. Should take you to Opal's YouTube site. It was intended to take you right to Speckles, but it somehow didn't. Speckles 1. Okay.
Now we'll close the front aperture down to 100. There's split 2000, 1500, 1000, and now we'll go back to 1500. I think it'll be a little brighter. And we'll put in the rear pinholes, and we'll go first to 2000. Won't be much of a change. And then 1000. Still not much of a change. 400. Now we're going to realign slightly. Bring that in. I think that'll be 200. And 100. And at this point you see it's almost just down to a point. Light. And the last one is 25. Let's see if we can pick that up. I think what we'll do next is increase the power a little bit. First.
Now you can just see one little spot
25
fluctuating.
for the pinhole. We'll go now to the pinhole of 100.
So now we're looking at one speckle, approximately.
200. 400.
And you should be able to watch those videos on your own another time. Okay. So, one of the things that happens is that the speckle patterns speed up as you go to higher scattering angles. And a good question is why. So why don't you think about why that might be? And that might be a good quiz question at some point in the future. But we'll demonstrate the effect here. You kind of have to remember how they were fluctuating in the first video. In the second video, we'll move to a higher angle. And you'll see, I think, even just from your memory, that they're faster. Let's see what happens. Oh, yeah? Great. I guess those videos aren't working as well. The links aren't working like I wanted.
Okay, so this is the same 500 nanometer latex sample. We've now moved to 40 degrees scattering angle. This is with open pinhole settings. I had to change my original plan, and different light intensities than previously.
None of that affects the speed of the speckles.
But clearly this is a much faster looking speckle than we had down at 15 degrees of scattering angle.
Okay. So what we had to do to make the speckles slow enough that we could see them was to choose large and fairly slowly diffusing objects and move to, if we really wanted them to be slow, we moved to low scattering angles. Okay. It's a lot of fun to look at them live, and you're welcome to do that. I have to supervise that experiment for safety reasons, but you're more than welcome to do that. Okay, let's talk about how we compute correlation functions, because I suspect that not too many of you have ever computed them, and that even though we said this equation is a recipe, we haven't baked that cake yet ourselves. So let's try to see how a correlation function will be built. Here's the equation down here again for our convenience. And what it says again is make a measurement at t prime, make a measurement at 1 plus 1 t prime plus 1 times delta t. So what we're going to do is we're going to divide our intensity versus time. Oh my goodness, this should be t prime there. I must fix it. I must fix it. Put a prime there. If I can find my if I can find my pen. Let's see if it'll let me do it here with a pen. That should be t prime. Okay, so what we're going to do is we're going to divide our times up into little segments delta t, and let's figure out how many pairs we can make that are separated by 1 delta t. Well, we can do compare 1 and 2, and remember, compare means take the product of 1 and 2, 2 and 3, 3 and 4, 4 and 5, 5 and 6. Well, there's lots of different pairs that are separated by 1 times delta t. Okay? So now that would give us one value of G2. And by the way, this little 2 here, I didn't tell you what that was. It's not an exponent. It means second order. Okay? And you can read some of the reference materials to see about why that is, but it's just a detail for now. Okay, so here we are. I have to prime this. again. And, oops, back. And how many do we make? How do we make the value of the correlation function at a lag time of twice delta t? Well, that would be 1 with 3, compare 1 and 3, 2 and 4, 3 and 5, 4 and 6, 8 and 10, 11 and 13, and so on. And you'll see that we have slightly fewer pairs to make the comparison with. Okay. The next one, we'll skip ahead. We'll do 5 delta t, and again, I have to prime that t there. You go ahead and prime it on your notes if you like. And now we're comparing 1 and 6, 2 and 7, 3 and 8, 4 and 9, so forth. And, we have fewer pairs than we did it, earlier on, but we still have quite a lot that we can calculate. And we sum all those together because that's what the integral says to do. Take all possible pairs, take the average of all possible pairs over the time scale of your measurement. Now, on the scale of this plot here, big T, our acquisition time, is, over here to the left it's in Florida, over there to the right it's in California, somewhere like that, So, okay, here's 10 delta T, and you can see we're really, we really have fewer pairs that we can make now. Okay, so originally we used to really do it like I showed you. We would calculate delta T, 2 delta T, 3 delta T, and we could get up to 256 delta T. It turned out the circuitry to do that was fairly easy to implement for people who knew electronics. And after a while, some mathematicians looked at the situation and said, you don't need all that. What you really want is delta T, 2 delta T, 4 delta T, 8 delta T, 256 delta T, and so forth. So you can build a simpler machine that, because of the exponential growth here in this lag time, covers an enormously wide range of lag times. Literally 10 decades of time, maybe more, can be covered by these new machines. The machines we use are made by a company called ALV in Germany, and they do sort of a quasi-linear multi-tau combination. Okay, it's really slick what they do. All right, well, anyway, we said that this thing is going to be an exponential decay. And here again, this is what we've seen before. We're going to measure this function, g2 of t. You might as well just call it y, who cares? Okay, and it's some baseline 1 plus an amplitude, coherence parameter, and then there's an exponential decay. That is q squared, which we know from the scattering angle and the wavelength of light, times the diffusion coefficient. So if we measure this decay rate here, we have a diffusion coefficient. And if we measure diffusion coefficient, we can get a hydrodynamic radius. We can finally get the size of the particle. And we can do that down to, 5 nanometers, even less. Okay, probably even 1 nanometer, somewhere in there. Depending on your solvent and temperature and some other parameters. But this is a very reliable way to get size, is to measure the diffusion coefficient from this correlation function. But it is an exponential decay. And that means that I'm going to tell you a little bit about exponential decays, because they happen not only in light scattering, but in all sorts of other methods like NMR, fluorescence lifetime, creep measurements. There's all sorts of measurements that are sort of exponential or similar to exponentials. Anytime you are doing an exponential measurement, you really want to make 4 plots. One of them is linear, the parameter y versus t in this case. Okay, linear on this scale, linear on this scale. Yep, that's how an exponential decay looks. All right, that's what we think of as exponential decay. Right? You also want to make a plot where you leave the y-axis linear, but you let the x-axis be logarithmic. You also want to make a plot where you do the opposite. You let the y-axis be logarithmic and let the x-axis stay linear. And then, just for good measure and symmetry, it's good to plot log and log. Right? Now, this is important because these views tell you a lot about what's going on in the system. For example, if I have a single exponential decay, exactly, this view here is going to be a wonderful, wonderful straight line. If it's polydispersed system, there's going to be multiple diffusers, and it usually will start to curve that way. Okay? If it's that you screwed up your experiment, it will curve that way. Okay? So that's some sort of experimental problem. The other thing that you need to know about just looking at these plots is that you can use them directly to estimate what the decay time, in this case, the inverse of twice gamma, that's your decay time, is. Right? What you're looking for is the 37% decay. Okay? If I have, let's just write this as y is equal to a e to the minus gamma t. Okay, let's just deal with that. Slightly different notation, but it's, I told you, they're all exponentials, they're all the same. You got to do the 4 plots, and then you got to be able to look at them and tell me what the correlation time is. What would happen if gamma, what would happen at t equals to 1 over gamma? If time is equal to 1 over gamma, then y is equal to a e to the minus 1. Right? So a, if t is equal to 0, okay, then we have a. A is the amplitude of the exponential decay. So what that tells you is that if you can locate the x-axis value, time, where the signal has decayed to 1 over e of its initial value, you have found 1 over gamma. Okay? And this is called usually the correlation time. Okay? Sometimes people call this a tau. They put in here a tau. Tau correlation, 1 over gamma. All right? So in other words, I have this exponentially decaying thing, and when I get to 1 over gamma, and by the way, 1 over gamma, 1 over e, 1 over e is 0.37, and that is very nearly 3/8. All right? So if I have a signal, if I have a signal that is decaying from a to 0, then I can easily divide by 2. That's a over 2. That's a over 4. That's that's 3/8 of a. If I can figure out where that is, I can draw a line over here and reflect it, just bounce it off that curve, and this must be my correlation time. So you don't have to do a lot of fancy computer fitting to figure out the correlation time of these experiments. And once you have the correlation time, you have gamma. Once you have gamma, you have the diffusion coefficient, just divided by q squared. And once you have the diffusion coefficient, you have the size. Okay? So in the bad old days of experiments, you could do that. And I'm going to encourage you to do that now, because you're going to get an assignment in this problem, in this section, where you get a bunch of these to analyze, and you can sit there and throw your fancy computer programs, or you can just go look for this, and you'll find that it works remarkably well, and you'll never forget it. And you'll be one of those people who can look at a signal and say, aha, the correlation time is kaboom, and just tell them what it is. This works really well in things like the Avrami-Mel equation for kinetics. So there's lots of places where you can use this kind of skill. Here again is another representation of that, and I'm going to let you look at that on your own in the slides, and you can work it out here on the side if you want. But we'll point out that it also turns out that if you're in this linear y logarithmic x representation, this 1 over e point, or basically the 3/8 point, is also where there's an inflection in that curve. You could also try to locate the slope of the, you could locate gamma from this semi-logarithmic curve. Here we've taken the natural log and plotted against linear time, and then the slope should give you the decay rate. Okay, and remember our decay rate is 2 gamma, 2 big gamma. All right, so that may take a little getting used to. It certainly took me a while to get used to that. All right, so gamma versus q squared. We saw in the videos that when we went to higher scattering angles, that the speckles moved faster. That means that they're going to decorrelate faster. That means that the correlation time is going to be shorter. The decay rates are going to be higher. Some of you may remember your diffusion and transport theory well enough to remember a little thing called Fick's law. Okay, and Fick's law in normal, you normally see it as something like, I really have to, come on, give me a pen. You might see Fick's law normally like something like this. X squared is twice diffusion coefficient times t. If you never saw it before, don't worry, we'll tell you about it. Watch those MSE 2001 videos that we put up there. We talk about that. I think they're called Introduction to Polymer Science in the set that you have on Opal. Well, in Fourier space, this is sort of like gamma. Okay, is proportional to q squared. Okay, so in light scattering, in inverse space, the light scattering is an inverse experiment, as we discussed. In an inverse space, these are both representations of Fick's law. And so what this plot is showing you is actually how gamma depends on q squared for two different spheres, both of which are exquisitely uniform in size. These are made for us by Dow Chemical, and those guys really know what they're doing. And you can see what great straight lines we have. And a lot of people will look at that and they'll say, oh, wow, R squared is 0.999. That's great data. And then I'll show them this plot and they'll say, wow, R squared is only 0.075. That must be sucky data. Well, it's the same data. Okay? So you got to be careful about how you interpret these correlation coefficients. A lot of people associate a correlation coefficient near 1 like that with perfection. But in fact, it depends on what you're plotting. This is a system which should have a straight line that goes through 0. If it goes through 0, then I take the y and divide it by the x, and I should get a flat line from the same data. And that's really a good way to test your quality of your system and your alignment. You want to test if something's really linear with a 0 intercept. Plot the y over the x versus the x, and if you get a flat line like this, it's pretty much sure that that is a straight line going through 0. So I like to see both of these. The slope of this black line is equal to the intercept of that black line. Since it's so flat, we might as well just take the average of all those points. Okay? And the same is true for the blue line. This flat, d parameter, this is our diffusion coefficient. If I were to invert that using the Stokes law that I just mentioned, I would be able to plot hydrodynamic radius versus q squared. All right, now it's time to talk a little bit about radii. This is a list of the radius of gyration that we get from static light scattering for various shapes. So here they are all listed. And you see that even things that bear no resemblance to a sphere have a radius of gyration. So a cylinder has a radius of gyration if length is much greater than the radius of the cylinder of L over the square root of 12. So you can define a radius for something that actually isn't spherical. It's no problem. Okay. Hydrodynamic radius is defined in a different way. We'll come back to that in a little bit. Here I want to introduce another concept about dynamic light scattering, which is that it is concentration dependent. And any radius or diffusion coefficient that you get from the thing, strictly speaking, should be extrapolated to 0 concentration. So you should make, let's say in this case, 1, 2, 3. That's kind of the bare minimum. Make the bare minimum of concentrations and extrapolate to get to the 0 angle, a 0 concentration diffusion coefficient before you go ahead and make that into a radius with your Stokes-Einstein relationship. I mentioned earlier that there are other techniques you can use for this. One of them is Dozy NMR. And look, it has a totally different concentration dependence. Again, this is the sort of subject that goes into 6751 polymer physical chemistry, but it's quite normal for diffusion coefficients in dynamic light scattering to go up with concentration, and it's almost always the case that they go down with concentration in Dozy NMR, and that's because they're looking at somewhat different kinds of diffusion. One is looking at mutual diffusion. What's dynamic light scattering is looking at mutual diffusion, and Dozy NMR is looking at self-diffusion. Okay, so they're slightly different. It's important then, if you really want to save some time, that you build an apparatus that can measure darn near 0 concentration. Look, if I could if I could make my measurements reliably way down here, even though I have hardly any polymer in there, if I can make a good measurement down there, I probably don't really have to worry so much about this extrapolation. So it behooves us to try to get instruments that can make dilute solution measurements. Okay, so that's what this point is making here. All right, I have a problem with people who say the size of an object comes from light scattering if they're not careful to identify whether they're talking about radius or diameter. Okay, oh my God, if it gets so confusing. So I say never say size, say radius or say diameter. If you want to, when you're converting your Stokes-Einstein relationship, take kT, Boltzmann's constant, times temperature, divide by 6 times the 6 pi, the viscosity, d. That'll give you a radius. If you want the diameter, divide by 3 here if you want. See if I care. Or multiply it by 2 when you're done. But for the love of God, be consistent about whether you're talking about radius or diameter. It's so confusing when you're not. All right, now I want to talk about what happens in a lot of black box dynamic light scattering instruments like the one they have over there in the OMCL at Georgia Tech, or in many other industrial labs will have a dynamic light scattering instrument that can only measure at one scattering angle. It works well in simple cases. Look, if I've got these particles made by these guys at Dow, it wouldn't matter what Q value I use. Look, it's completely independent of Q. Look at the correlation coefficient. It's independent of Q. I could pick that Q. I could measure maybe that's 90 degrees. Maybe that corresponds to 90 degrees. This one corresponds to 25 degrees or something like that. It would not matter. It would not matter if I'm doing that. I have any angle I want. I could pick one arbitrarily, but very few systems really do that. In general, you want to make measurements at multiple scattering angles. And here's an example of influenza virus, and it's made by nature. Usually nature does a good job. It turns out nature has no particular reason to make influenza virus particles uniformly. Okay, it turns out that it's quite happy to just make them willy-nilly, any old size at once. We, in our synthetic labs, could make uniform particles, and they're beautiful. It doesn't depend. We could measure those at any angle. But a lot of cases, you will get an apparent diameter that increases with scattering angle. The reason for that is polydispersity. Okay? Remember from our static light scattering, we learned that large particles scatter better to low angles than they do to high angles. So if we're looking at a high angle, we're seeing preferentially the small particles, and of course they move faster. That's what's going on here. So you have to make that correction. You have to do multiple angles. Okay. Nevertheless, you can do really cool things, even with a single angle experiment. This is showing influenza particles, both the intensity, okay, and the radius, okay. So what you see happens in the case of this particular influenza is when its pH is dropped, it suddenly increases its size, and then the intensity starts to rise. So what it does is it pops open, and then after it pops open, they start to aggregate. Okay, so you could imagine something like a little ball that, you know, pops open and exposes a bunch of Velcro, and then as it diffuses around, the Velcro attaches to the other particles. So that's kind of what happens there. DLS is a really good way to follow that kind of experiment. Okay, so this brings me to the case of polydispersed samples in DLS. It does respond in a useful way to polydispersity. It's kind of complicated. What we often do is we take that G2 that we measure and we realize that it's actually the magnitude of what's called G1, the electric field autocorrelation function, which you cannot usually directly measure. You can usually directly measure this one. You can get that one by simple, you know, algebra. Once you have it, that G1 is the sum of what's going on for all the things in the system. So here's one diffuser diffusing with decay rate gamma 1, another diffuser with decay rate gamma 2, another diffuser with decay rate gamma 3, and so forth. Now the amplitudes that go into this G1 are proportional to concentration times mass times the particle form factor, okay, which is a function of the scattering vector and the size of the particle. Okay. By the way, this relationship here, it's a famous relationship. It's called the Siegert relation, and yet again, it's something that could be proved in 6751 class. Okay, so I mentioned earlier that when these semi-logarithmic plots, you see this as a log scale on the y, a linear scale on the x. When it curves smoothly upward like that, that's a good indicator that you have a mixture of sizes from big to little. All right? And one of the things that you can do about that, the easiest thing you can do about that is try to fit the very initial slope. And this is actually called cumulance analysis, and I encourage you to read some of the reference materials about it. It's a very confusing notation. We could fit the initial behavior of this line to a straight line if we only use those points. Or we could take more points and start using a quadratic. Or we could take even more points and start using a cubic equation. But in all cases, whatever we do, whether we use a linear or quadratic or a cubic equation, in all cases, we're really interested in that initial slope. That's a well-defined thing. That initial slope gives you a hydrodynamic radius, okay, which I have really yet not told you what that is, but I will in a minute. That is 1 over the z-average of 1 over the hydrodynamic radius of each of the particles. Oh my goodness. All right, so that's something we can usually do pretty easily. So this is kind of outlining the choices here. So here's our instrument. And this is supposed to represent the correlation function. And we can do cumulance analysis, that's what I just told you. Or we could do a multi-exponential fit to that data. We could try to fit the data to multiple exponentials, so you get to practice those skills. Or we could do an inverse Laplace transform on the data. We can basically, here what we're doing is we're measuring this G1 and we're asking the question, what is A as a function of gamma? Well, that's a nice mathematical relationship, but the very instant there is any noise, and I do mean any noise, on G1 of t, then A of gamma becomes very difficult to determine. 0.1% noise, you're doomed. Okay, so there's limits to what you can do here. But nevertheless, you can do some simple things. So for example, you can actually try to calculate a distribution of sizes. Okay, it's a pretty complicated procedure here to do that inverse Laplace transform with the distribution of sizes, but it's doable. What happens is you measure G2, minus the baseline, take a square root, now you have G1. Now do an inverse Laplace transform of that, now you have a set of A's and gammas. You convert the gammas to D1s, that's reliable. Take the gammas, divide by Q squared, now you've got a set of D's. So you've got amplitudes versus diffusion, so now what are you going to do? Okay, well, I can get from the diffusion coefficients to hydrodynamic radius, which I still haven't exactly told you what that is. There is, if you're lucky, a good relationship between the radius of gyration and the hydrodynamic radius. Okay, typically that's related by a factor x, which is about 2/3, roughly speaking. And now I have a set of amplitudes and radii. Oh my heavens, now let's see, over here, here's my amplitudes. Okay, so I could, if I wanted to, I could divide these amplitudes by the form factor, which I could get if I know the shape. Well, how would I know the shape? It really helps to know the shape. We usually know the shape from things like this relationship. If the diffusion is alpha m to the minus beta, this is going to tell you a little bit about the shape. For example, beta of a half here should be polymer in a theta solvent. Okay, this could be viewed as a Mark-Huink type relationship. Those of you who remember your intrinsic viscosity theory, this is a Mark-Huink type relationship. Anyway, at this point I can convert to molecular weight on this side. So over here I'm evolving some molecular weights, and over here I'm evolving some sort of corrections to get from these amplitudes into something like proportionalities of concentrations by mass. Okay, well, once I know the mass, I can get from concentrations times mass. I can divide out the mass, and I have separately the concentrations and the masses. So in principle, then, at the end of the day, I can come up with a plot of concentration versus mass, or even number versus mass. So it's a very messy situation. You would not do this unless you had to. But lots of times you kind of have to. I'll give you a case where it's really useful to do this. Suppose it's your job to figure out the molecular weight distribution of Teflon. Okay, well, you're too late because the guy already did that. He did it by dynamic light scattering because nobody wanted to put Teflon into the gel permeation chromatography instrument. Okay, so this is the kind of case that can happen. Another good case that's this is very useful, believe it or not, is simple polyolefins. This technique is way underutilized for measurement of simple polyolefins. Okay, so of course, fortunately, there's software that does this for you. There's intelligent software, meaning that you have to be intelligent, and it will produce a distribution like that. That's supposed to be something like a size versus concentration distribution. Okay, here's an example where somebody used that. You'll see it all the time, these plots. And usually the people who are doing this have no idea of what they're talking about. And they may report ridiculous things like sizes that are smaller than an angstrom or something like that. But this is an interesting study where they used dynamic light scattering to see what was going on inside of BHT stabilized tetrahydrofuran, which is a common solvent. It turns out there's a little structures in there that people didn't even know about. So that was kind of cool. Well, finally, what does this hydrodynamic radius really mean? Okay, I'm going to just let you look at this box as long as you want, but let me just tell you. It's a little bit like RG, radius of gyration, in the sense that it doesn't have to be a spherical object to have an RH. Okay, we said that a rod had an RG. A rod also has an RH. Okay? But what it is, it's the radius of a sphere that would be diffusing as fast as your object is going, no matter what the shape of your object is. Suppose you have a cube over there in the other side of campus. There are people making little cubical silver particles. They're making little triangular silver particles. All sorts of things like that can be made. You can measure their diffusion coefficients. They go a certain speed. They have a certain diffusion coefficient, I don't know, 10 to the minus 7th square centimeters per second. Okay? The hydrodynamic radius of that cube, is the size of a spherical object going 10 to the minus 7th square centimeters per second. Okay? Right? So it's defined through how fast the object is going. Okay? That's what you need to know. This summarizes some of the differences between static and dynamic light scattering. Okay, molecular weight. DLS can do it, sort of. You need a Mark-Wink type calibration. See, we just had it here. There it is. If you've actually made the connection between diffusion and molecular weight, you can measure the diffusion, get out the molecular weight, just like intrinsic viscosity would. Molecular weight distribution, yes, with some notes. Static light scattering, not so easy. Sometimes maybe. I don't know. Weird things could be thought of, I think. Virial coefficient, no. Static light scattering, yes. So you can't get a direct virial coefficient very easily out of DLS, but you can still tell whether the polymers are aggregating or not, or whether they're prone to or not. It's just not as clean as SLS for that. Size, yes, absolutely. And in a wider range, too, especially on the small end. But you have to deal with a hydrodynamic radius. Here you get RG. Size distribution, yes, with some things. Also, yes, with some notes. Correlation length, that's a polymer physics thing, so we won't talk about that, but you can get that. Aggregation, yes. Yes. Translational diffusion, yes. No. Rotational diffusion, yeah, it turns out under some circumstances you can see how quickly a molecule is rotating by DLS. That's actually very useful because rotational diffusion is much more sensitive to shape change or to differences in length or dimension than is translational diffusion coefficient. Okay, so they're both useful, and really they should both be done at once. Okay. Well, one thing you may be wondering, we started to wonder a few years ago whether it's possible to do all these things quickly using multiple angles. And we mostly have talked, the machine I showed you so far is a machine that just measures one angle, then you change to another angle and you make another measurement, then you change to another angle and you make yet another measurement, and so forth. And it's very slow and tedious, but boy, is that machine got great optics. Okay. Detectors are expensive in this game because they have to perform well. They have to be able to count millions of photocounts, or a million or more photocounts per second without screwing up. And so this costs money. But in fact, actually, the prices have come down a little bit, so it's possible to think about these multi-angle, multicorrelator dynamic light scattering instruments. And our current best at that is described on this thing. And you'll see it in action, so I'm probably not going to lecture on this too much, but you can watch this YouTube if you want, beginning at 315 seconds would be my advice. And you'll see that there are a bunch of different semi-log plots here, one for each of 8 different angles. And we used the Laplace inversion software to calculate a size distribution. We gathered all 8 angles. The answers agree for all 8 angles. And we did all that, oh, I don't know, probably in 2 minutes or so. Very few places on the planet can do that, and this machine should be used anytime you're going to go use one of the simple, cheap black box instruments over there in OMCL or someplace else. You want to come measure it here on this instrument first to tell you if you can get away with just using that one angle. Sometimes you can't, in which case we're happy for you to go use their machine. Okay, there are some special topics in dynamic light scattering involving depolarized light scattering, and I'm going to run through these really quickly. And there's even now a version of dynamic light scattering done with X-rays, and it's called XPCS. PCS means photon correlation spectroscopy. A lot of people call DLS PCS. Okay, it's almost synonymous. But when it's done with X-rays, it's a little different. Okay, so this is what goes on in going all the way back to our study of static light scattering. If I have a laser beam and I have a point scatterer here, it sets up this sort of donut-like radiation pattern. And that's what happens for most objects that have no optical anisotropy. But there are objects that do have optical anisotropy, and what they do is they kind of rotate the response, okay, and produce a little bit of depolarized scattering. So I send in a vertically polarized incident light, and I look only at the horizontally polarized light on the, in the detector, and lo and behold, there's something there, because the molecule kind of grabbed the light, and when it re-emitted it as radiated light, it gave it a little bit of a horizontal component. Now, if the molecule continues to rotate, well, its ability to grab or to re-emit changes with that rotation. So that's how we can pick up on rotational motion. And this is showing that idea here. Oh, look, the animation still works. Amazing. And not only does it work, it's going brighter and dimmer as the object rotates around. Okay, you could make a kind of a relation of this to what you see when you look at sphere lights in a microscope. And notice that it's brighter at 45 positions than it is at the 90, 0, 90, 180, 270 is brighter, is dimmer than 45, 135, and whatever comes next. Okay, so this lets us measure that rotational diffusion. Okay, and we actually applied that to tobacco mosaic virus. So I've kind of come full circle. I started with tobacco mosaic virus. Now we're back to it. So that must mean we're getting to the end. So you can actually make these rotational diffusion coefficient measurements. And you can still make the translational diffusion coefficient measurements. Another sample that does this very well besides TMV, tobacco virus, is PTFE latex particles, which are great things for depolarizing light. And your equations change. If I use a vertical incident light and detect vertically the vertical component of the scattered light, that's called big V little v, gamma big V little v, is what we see in Q squared D trans. But when I look at the horizontal light, I have gamma HV, which has that translational and diffusion coefficient all right, but also sits up on a baseline of rotational diffusion coefficient. Okay, so I can do both. And so this is how these gamma versus Q squared plots look. Gamma HV has a finite intercept. And now, if I were to take gamma HV and divide by Q squared, where I'm expecting for most systems to have a flat line, what do I get when I do this plot? Why don't you think about that a little bit? I can take and I can actually convert either the translational or the rotational diffusion coefficient. If I know the radius, I can actually calculate the viscosity of the fluid. So here we're actually doing things backwards. Normally we say, okay, so we know the viscosity of the fluid. What's the size of that particle? There could be situations, let's just take as an example, polymers dissolve in a supercritical fluid, or polymers dissolve in some tiny little chamber. And there you might want to know, what's the viscosity in that tiny little chamber? I can't get my rheometer in there, but I can put in a probe particle of known size, see how it's DLS. Well, DLS will tell me how quickly it's going. I'll solve that for a viscosity. We'll call that a microviscosity because we measured it on the micro scale. So eta mu is microviscosity. Lots of people have had these ideas, okay? Now what's really interesting is that you can take the ratio. If you can measure two transport coefficients, it's kind of like a rule. If you can measure two transport coefficients, you almost have done like a thermodynamic level experiment. You've certainly eliminated something. And I measure the translational and I measure the rotational, and look, I come up with a radius without ever needing to know the viscosity. So I could actually not know the radius of my particle, not know the viscosity of the fluid it's in, calculate the radius. Then I could take and put that radius back into these microviscosity equations and calculate the microviscosity. I could start knowing nothing and wind up knowing everything. That's kind of cool. Okay, DLS can measure very small volumes, okay? With the help of some people at UT Southwestern Texas Medical Center, we once did an experiment. These guys were looking at these coacervate phases. A lot of interest in coacervate phases now for, trying to understand how various things happen in nature, how various diseases happen. They're like phases, only they're not really phases. They're very small. They're sort of nebulously defined type things. Bretman Group is looking at them here. Many people are looking at them elsewhere. But usually you don't have them in great quantity. So we were approached by a guy at a medical school who said, we got this Nature paper, and the reviewer said we needed to do it at multiple scattering angles. They don't believe our single angle DLS, and we heard you were good at this, so could you help us? So we did. We did this really simple experiment for these guys, and that paper's been cited more than 1,000 times in 10 years. Almost every week it gets another citation. It's really remarkable. So you can use very small volumes, is the point. I told you I say a little bit about X-ray photon correlation spectroscopy. What it is X-ray implies pretty high spatial frequencies. So that means you're looking at short distances. The detectors are not incredibly fast like the detectors we have in visible light scattering. So if you need to look at something that's moving not very far and doing it pretty slowly, this is a pretty powerful technique. And you see the same kind of curves that we're used to seeing by now. And that's it. Thank you very much.